Hello, everyone, and welcome to session D, paper session D. The topic is networks for large language models. I'd say that to call this a hot topic in interconnects is almost a bit of an understatement. And I found it comical that I believe the second paper's first sentence describes it as a scorching topic, which I think is an entirely appropriate adjective. So with that, our first paper is the case for domain-specific networks by Dennis Abts from NVIDIA and John Kim from KAIST, the Korean Advanced Institute for Science and Technology. With that, I'll start the video. We have Dennis here. So as a reminder, please submit all your questions to the Slack channel, and we will take those at the end. And Dennis is here to respond as they come in. And here we go.
Hello and greetings from Hot Interconnects 2023. My name is Dennis Abts. I'm a research scientist at NVIDIA. And today, along with my co-author, John Kim from KAIST, we would like to present the case for domain-specific networks. Domain specialization is a common idea, and we see it in our daily lives. It is purpose-built products that are solving a narrow set of tasks. They have unique capabilities and really are striving for uncompromising performance on this very limited set of tasks. An example of which is an airliner such as the Boeing 737, which is designed for capacity, reliability, and both space and fuel efficiency. Similarly, an F-35 is a domain-specific product designed for performance and maneuverability, as well as offensive and defensive weapon. So we're in this domain of designing products that are specialized for a specific purpose. And the reason why this plays a central role is because recently large language models have essentially been a turning point since the introduction of the transformer neural network model in 2017. Networks. Transformer is a very generic and efficient differentiable neural network. Us to apply it to a variety of application domains, including question and answering, such as chatbots, as well as, for example, among others. This popularity has really driven some design parameters, as well as the exponential growth in computing resources. As we see over the last 6 years, there's been a dramatic increase in the size of these models as we went from hundreds of millions to hundreds of billions and even approaching trillions of parameters, requiring more memory bandwidth and more scale, more accelerators in the system. So these trends have really been driving our system designs to take advantage of this larger scale. And the benefits here is that as scale improves, so too does the accuracy of the model, as well as new capabilities that arise. For example, this is from the ChatGPT-4 system card that was part of the technical paper. It shows these emergent properties that only arise with additional scale. All of this has really ushered in a new golden era for computer architecture, driven by hardware-software co-design to solve these very narrow tasks associated with deep learning. And these tasks have spanned from instruction set design to network optimization. And today we're going to talk more about the network optimization part and how we can take advantage of abundant parallelism in deep learning. At the heart of this is a domain-specific processor. And this, of course, is a continuum. And on one end of that is flexibility driven by general purpose CPUs, which are capable of solving a wide range of problems. And as you progress from left to right, you're exposing more concurrency through SIMD or SIMT execution, like in GPUs, as well as customization and specialization afforded by FPGAs, and at the extreme end are custom chips or application-specific integrated circuits. And these ASICs allow us to exploit all the parallelism and do so efficiently, both from a cost and an energy perspective. Similarly, there's a similar type of speciation that we can take advantage of in the network, and we want to differentiate that, trading off generality and flexibility for purpose-built specialization that allows us to achieve the highest efficiency as measured by performance per dollar. There's been a wide number of designs across this space, starting with the most ubiquitous Ethernet and InfiniBand products that are common in most cloud providers, to more custom interconnects such as Cray HPE's Slingshot and NVIDIA's NVLink and NVSwitch. At the opposite extreme, the efficiency extreme, are highly custom networks such as the IBM Blue Gene Q multidimensional torus and other scale-out networks that are designed for efficiency on physics simulations, things that can embody and take advantage of 3D domain decomposition and nearest neighbor communications to exploit that communication pattern. Examples of these include the third generation DE Shaw Anton, now in their third generation, designed for custom design for molecular dynamics, again, taking advantage of torus for nearest neighbor communication. The Tesla Dojo, which is a hierarchical mesh, again, exploiting nearest neighbor communication for tensor parallelism and data model parallelism, as well as more traditional like Google's TPU, exploiting a twisted torus, again, nearest neighbor communication, as well as hierarchical all reduce. And then Grok's scale-out tensor streaming multiprocessor, which uses a synchronous communication model to reduce the amount of communication costs for global synchronization. All of these have been very novel implementations and have different properties, all of which seek to exploit new levels of concurrency and efficiency. This has led to domain-specific supercomputers for AI, really motivating us to build systems for this, which includes both the processor and the interconnect. Really, communication and computation are two sides of the same coin, and we're just recognizing this as the necessity to carry that specialization into the network itself. There's been a number of novel implementations from the Google TPU, now in its fourth generation, the Dojo Tesla's Dojo supercomputer designed for training vision systems, as well as the DGX H100 and SuperPod for large-scale training. A cloud service provider like Meta uses Xeon EX, a custom network and system designed for training recommenders, and a novel implementation of a wafer scale engine that exploits large degree of nearest neighbor communications on the wafer itself. All of these have been very novel implementations designed to exploit new levels of concurrency. And all of this has been really driving our system architecture, that is really building systems that are geared to be able to scale, to take advantage of the larger parameter space in these neural networks, along with the increased computational intensity, requiring more endpoints for training a distributed learning model. Lastly, there's been a larger training data corpus as we've trained these systems on curated data that is on the order of 1 trillion tokens. So there's a lot of data, and that puts stress on the IO subsystem as well. And this has really driven a number of these recent supercomputers, including Google's and Tesla and NVIDIA supercomputers. This has really spawned a wide range of innovation in hardware accelerators, as deemed from the recent Cambrian explosion of domain-specific hardware accelerators, a number of companies that are producing unique products in this area, including companies like GraphCore, Cerebras, TenseTorrent, Grok, and Sambanova, including incumbents like NVIDIA as well with their Hopper GPU design. All these systems were designed prior to 2017, when the inaugural paper, Attention is All You Need, was introduced, the transformer model architecture. So these systems were designed in an era with emphasis on convolutional neural networks, or CNNs. As a result, some of the systems have very limited space for these on-chip weights to exist. So we need to rethink and reimagine our system designs to take advantage of this rapid adoption of transformers. We need more memory capacity and memory bandwidth. Technologies like HBM3, for example, providing several terabytes of main memory bandwidth. We're also able to take advantage of hardware that can exploit regular sparsity. Networks that use ReLU as an activation function often produce very sparse activation maps, and we can take advantage of that sparsity. Of course, there's also efficient lookups for what are the positional encodings of the embedding vectors. And these embeddings are often put a lot of stress on the memory system because they're very sequential. You have to repeatedly look up vectors and then combine them to form the embedding vector. And this workload is dominated by vector and matrix multiplication, as well as GEM, a generic matrix multiply. So why do we even care about domain-specific networks? They've been a key enabler for these machine learning supercomputers and provide unique capabilities that can exploit the different dimensions of parallelism. We'll talk a little bit about that shortly. And they also look to minimize the end-to-end latency. And they do so by minimizing the communication protocol overhead and taking advantage of the abundant path diversity that these networks afford. In addition, they use specialized hardware to improve the efficiency of reduction sum, all reduce, a collective that's used to share gradients across all the parallel learners. In addition, we have efficient gather and scatter support in the memory system, all of which allows us to better handle the common communication patterns in these deep learning workloads. So as an example of such speciation, a differentiation in the network, one of the features is gather and scatter support. So we can indirectly give an address for every element, even if those addresses are non-contiguous in main memory. And that allows us to efficiently fetch the elements of the vector from the memory system, including an asynchronous offload engine for tensor memory acceleration. In a tensor memory accelerator, we're describing the shape of the tensor in terms of its width and its height, as well as its padding and stride. And then the memory system fetches those elements automatically without involving the SM core. That prevents us overloading our ALUs to do effective address calculation, adding up essentially the different dimensions of the tensor to get the right address. And this reduces our end-to-end latency to do a remote memory copy, for example, to copy a tensor from one GPU to another. So all of this is to say we want to exploit new levels of parallelism that are common in machine learning, and specifically deep learning neural networks. They take advantage of pipeline parallelism, which shards the layers of the model across adjacent processing elements so that we can efficiently pipeline their execution. And we do this on a collection of processing elements that are nearby. They're near to each other. In other words, you're really trying to spread that computation across nearest neighbors to exploit communication and packaging locality. At the next level, we want to exploit tensor level parallelism, where we slice our large tensors into smaller pieces and then give those as inputs across these parallel pipelined models, all of which entails one element of a distributed learner. And we take those distributed learners and we place them across a large scale system, and they learn in parallel. And we use an all reduce to exchange our gradients and make sure that all the learners have an accurate and up-to-date set of weights. We're able to exploit locality at various levels. In particular, the memory system is a good example. And programmers are very clever about uncovering parallelism and moving mountains to be able to exploit that locality. As an example of this, the NVIDIA Hopper introduces a new layer of hierarchy, the thread block cluster. And in this thread block cluster, SMs of the GPU can efficiently communicate through a common shared memory layer. This allows us to implement very low latency communication between the SMs and efficiently spread the layers of a model across the processing cores. Likewise, at the distributed parallel processing across the wider system, we look at more efficient communication protocols other than the common RDMA-based communication protocol, which entails a multi-step process to initiate a transaction from a remote processor and take that result and then operate on it. As an example of such, the Grok tensor streaming multiprocessor uses a synchronous communication model to push data across the network at the right time when it's needed, all of which are governed by the timestamps and a synchronous communication model so that you don't incur any idle time waiting for the data to show up. Efficient synchronization across the system is so important that there's often additional hardware added. For example, as the system size increases, so too does the global synchronization cost, often scaling directly with the diameter of the network. An example of this is a common primitive used for a reduction sum collective, which is a all reduce. And an all reduce allows the systems to share their weights efficiently across the entire system. This all reduce stresses the network bisection bandwidth. So as a result, we're motivated to put additional hardware in the switches themselves, such as the NV switch and NV link, which implement in-network collectives to be able to provide hardware support to directly execute that all reduce. In addition, pipeline parallelism exploits nearest neighbor or point-to-point communication for efficient pipelining across the model. So as a result, we really want to have small messages that we can quickly launch into the network and overlap communication with computation. Another example of this specialization is a hierarchical all reduce, which exploits the different dimensions of the network topology and packaging hierarchy boundaries to efficiently reduce across these different dimensions. For example, you may do a reduction in the X dimension, followed by a reduction in the Y dimension, and then lastly, a reduction in the Z dimension, and then summarize that cohort across those three dimensions. All of this reduces the amount of volume that is in the network. These all add up to be superpowers for deep learning. These multiple dimensions of parallelism through the memory hierarchy, network topology, and system packaging allow us to build really efficient supercomputers with fine-grained communication to reduce the synchronization overhead and to exploit model and tensor parallelism. The custom hardware for mapping tensor shapes to memory, such as the TMA and gather-scatter support, have proved to be really important in these types of workloads. So in conclusion, we want to design a special purpose network to enable these AI supercomputers with the goal of maximizing throughput, bisection bandwidth, global bandwidth, while still minimizing end-to-end latency, all of which are driven by efficient communication protocols with low overhead and low synchronization cost, as well as synchronous or asynchronous communication modes that allow us to take advantage of and reduce any barrier waiting times. Lightweight network packets allow us to very efficiently extend the local memory system with loads and stores and atomics into the global memory system across the network fabric so that we can efficiently do loads and stores to remote memory. Lastly, unordered messages allow us to adaptively route the messages as they flow in the network so that we can spread the traffic across available path diversity in the network. We can exploit multiple global links and spread the traffic and load balance those links to avoid contention. And single-sided messages really reduces the amount of end-to-end latency, all of which are in service toward reducing the overhead to all reduce at scale. So I hope to have motivated and giving you some examples of the type of network specialization, the motivation for it, how we exploit multiple levels of parallelism, and the benefits to it. We want to thank you for your attention and hope you enjoy the rest of the conference.
All right, very nice presentation, Dennis. We have a question in Slack, so with a great answer, feel free, please, to ask more. And I actually have one if you're available, Dennis. So it seems to me that the takeaway is there's a whole spectrum from general purpose to very domain specific architectures out there, and there are trade-offs, but also, you know, sort of extreme benefits, particularly for something as important as AI and LLMs, to embrace domain specific. Do you think that applies to, say, how we program systems? For instance, you know, in software programming models, do you think we should also embrace very unique, say, programming models to support domain-specific systems?
It's a great question. So domain-specific hardware certainly gives some superpowers, but software techniques like abstraction really tried to hide that complexity. And that's really where you want to be, so that from one generation to the next, you don't develop brittle systems that frankly get fragile with age. And so this domain specificity really helps, but it's also something you have to guard against to prevent leaky abstractions and prevent it from kind of exposing itself willy-nilly to the programmers. You want them to benefit from it, but you don't necessarily want them to move mountains trying to figure out all the different bits and locations. So having good abstractions in place helps to guard against that kind of generational bit rot, and also makes it more general purpose to help your programmers be more, well, productive.
Yeah, that's very well put. Well, thank you very much, Dennis. And yeah, I hope you stick around. I hope we get some more questions in the Slack chat channel. So thanks again. And let's move on to our next talk. So we have from University of California, Merced, HOTI, with a paper entitled Performance Characterization of Large Language Models on High-Speed Interconnects. His co-authors are also from UC Merced and someone from Amazon Web Services. So with that, yeah, you have control, Hao, and please take it away.
Hey. Thank you so much, David, for the introduction. So let me start my presentation here. Good afternoon, everyone. Today, I'm excited to present our work on the performance characterization of large language models on high-speed interconnects. This research was conducted by our team at the Department of Computer Science and Engineering at the University of California, Merced, in collaboration with the Amazon Web Service. Our study is part of the ongoing effort here at the Parallel and Distributed System Lab at UC Merced. And my name is Hao, and I would like to acknowledge all my co-authors, Liuyao, Weicong, Zhen, and also Professor Xiaoyi Lu for their contributions to this work. So now let's go to the details of this paper. To start with, let me give you an overview of what I will be discussing today. My presentation today is structured into 4 main sections. First, I will provide an introduction and background on large language models and the role of high-speed interconnects in their training. Next, I will discuss the characterization methodology that we use to evaluate the performance of training these models on different interconnects. And after that, I will present our evaluation results, highlighting the key findings and the insights from our experiments. And finally, I will conclude the presentation today with a summary of our contributions and also a short discussion of potential future work in this area. So now let's start with the introduction and the background. Let's begin with an introduction to the large language models, or LLMs for short. So LLMs are powerful machine learning models that can generate human-like text and perform a wide range of natural language processing tasks. In recent years, we have seen the rise of the transformer-based models such as the GPT, BERT, and the T5, which have revolutionized the field of the natural language processing. And these models have found applications in various domains, including language translation, text generation, sentiment analysis, and more. So I believe everyone here has ever used or at least heard of the powerful ChatGPT, which is based on the GPT 3.5 from the GPT family. So as we can see from the figure on the right, compared to the other online services, the large language models have been super hot since its debut, and the ChatGPT only takes 5 days to reach 1 million users. However, on the other hand, the large language models come with their own set of challenges, both in training and inference. So these models are big, so they usually consist of millions to billions and even trillions of parameters, so which will require a substantial computational power and memory to train and deploy them. And then next, let's turn our attention to the high-speed interconnects, so which play a crucial role in the training of those large language models. So high-speed interconnects come in various types. So some of the popular used ones include the Ethernet, the InfiniBand, and the omnipath. And their primary function is to facilitate the communication among the GPUs and the computer nodes, as well as to reduce the communication latency. The impact of the high-speed interconnect on large language model training is significant. So they can enhance the performance, improve the training scalability, and increase the training efficiency. So however, there are also challenges associated with their use, such as their utilization optimization and the compatibility with different models. So I would also like to draw your attention to the interconnect system share as of June 2023. So as reported on the top 500 website, so which is shown on the right. So this information provides insights into the current state of these high-speed interconnects in the top 500 HPC clusters. So as we can see, Ethernet and the InfiniBand still definitely takes the majority among them. So this is another reason why we include Ethernet and the InfiniBand in this work. In this slide, I will briefly discuss the concept of distributed training and the role of high-speed interconnects in this process. So distributed training is a technique where we partition models or data across multiple computer nodes, allowing us to train the models in parallel. And this approach is particularly useful for training big models like the large language models. High-speed interconnects such as the InfiniBand and the high-speed Ethernet play a crucial role in the distributed training. So as we mentioned, they can facilitate the efficient data transfer among the node and the GPUs, enabling fast and scalable communication. So as you can see from the figure on the right, almost all the deep learning frameworks utilizing the communication libraries like the NICO, they all rely on the high-speed interconnects for the efficient communication during the distributed training. So therefore, in this paper, our focus is to evaluate the training performance of these large language models over different high-speed interconnects and different communication protocols. Let's take a closer look at the large language models that we selected for this study. So first, we have the generative pre-trained transformer, or GPT in short. GPT family uses a decoder-based architecture and is known for their capabilities in text generation, summarization, and text completion. So in other words, they are good for generating new contents. So I believe you must be familiar with some well-known variants of the GPT family, for example, like the GPT-2, GPT-3, and the most recent one, GPT-4. And the second one is BERT, which stands for the bidirectional encoder representation from transformers. The BERT model employs an encoder-based architecture and excels in tasks like text classification, named entity recognition, and also the sentiment analysis. So some example variants of the BERT include the BERT base and the BERT large, and they are good in summarizing existing contents. And thirdly, we have the T5 model, the text-to-text transfer transformer. T5 incorporates both encoder and decoder-based architecture, and is recognized for their text-to-text transfer learning. And it is widely used for machine learning translation tasks, question answering, and also sometimes document classification. So with that, let's now move on to our second section of today's presentation. In this section, I will discuss the characterization methodology that we use to evaluate the performance of these models on high-speed interconnects. I will explain how we approached this study and the dimensions we considered, and also the specific models and the interconnect technologies that we explored. So let's see the details. The figure on the top provides an overview of the methodology that we used to characterize the performance of these large language models on high-speed interconnects. Our approach involved 3 dimensions, including the workload, the scalability, and the interconnects with the protocols. So for the workload, we focused on the 3 large language model architectures we just mentioned, the encoder-based models, the decoder-based models, and the both encoder and decoder-based models. So for the scalability, we evaluated the training scalability of these models by considering both strong scaling and weak scaling aspects. And in terms of the interconnect and the protocols, we explored the RDMA, IPOIB, and the TCP/IP. To quantify the benefits and the limitations of each interconnect or protocol option, we measured some key metrics, such as the communication time, the interconnect bandwidth utilization, and these metrics provide valuable insights into the performance characteristics of these selected models on different interconnects. So with this methodology, we aimed to gain a comprehensive understanding of the impact of these high-speed interconnects on the distributed training of these large language models. Let's take a closer look at the specific models that we selected in this study. So in this paper, we evaluated 4 models, GPT-2 medium, GPT-2 large, BERT large, and T5 large. Each model has its own architecture, number of layers, hidden size, number of attention heads, and also the number of parameters. So for example, the GPT-2 medium, which is shown as the first row in the table, has a decoder-based architecture with 24 layers, and it has a hidden size of 1024, and it has 16 attention heads, and it also has 345 million parameters. On the other hand, a second example is the T5 large, so that is shown on the last row in the table. So it has an encoder and a decoder-based architecture, and it has 24 layers, a hidden size of 1024, and it also has 16 attention heads, but it has 770 million parameters. So in our study, we also leveraged the Megatron LM framework for the distributed training, so which can provide us with the efficient and scalable implementation of distributed training algorithms and methods. So as for the data set, we utilize the ENVIDIA data set, which is a large-scale data set derived from the English Wikipedia. This data set contains vast text documents spanning diverse topics and genres, so making it a representative example for our study. So with this setup, we conducted a series of experiments to characterize the performance of training these models with different high-speed interconnects. So now that we have discussed the characterization methodology, let's move on to the next section of the presentation, where I will present the evaluation results. So in this section, I will share some key observations and the insights from our experiments, highlighting the impact of those high-speed interconnects on the training performance of these large language models. Let's see the evaluation results. So this is the experimental setup that I used for the evaluation. the experiments were conducted on the NSF-funded Pinnacles cluster here at UC Merced, which consists of 8 GPU nodes. And for each GPU node, it is equipped with 2 Intel 28-core Xeon CPUs running at 2.0 GHz. And each node has 256 GB of DRAM. And most importantly, each node has 2 NVIDIA A100 GPUs with PCIe. And all the compute nodes are interconnected via 100 Gbps EDR InfiniBand with RDMA and 10 Gbps Ethernet. So for the evaluation, we used up to 4 GPU nodes, i.e. 8 GPUs in total. The software stack included CUDA, PyTorch, Nico, NVIDIA Apex, and also the Megatron LM framework. And the training approach involved data parallelism with floating point 16 precision training. So regarding the batch size configuration, for strong scaling, the global batch size was set to 16. And for the weak scaling, the macro batch size was set to 4. And no matter in which case, the relation between the two is that the number of GPUs times the macro batch size will be equal to the global batch size. Okay, then let's take a look at the evaluation results for strong scaling first. In strong scaling, we fix the global batch size and increase the number of GPUs. So we show the training time breakdown for the 4 different models, and we compare the results of using the 3 different interconnects or protocols, the RDMA, IPOIB, and the TCP/IP. So within the breakdown, there are 3 components that take most of the training iteration time. So they are the forward compute time, backward compute time, and the backward communication time. So which means the parameter all reduce. I would like to highlight 2 key observations from this figure. So the observation 1 is that the forward and backward compute process in the large language model training can achieve a strong scaling efficiency of around 56% and 71% respectively. And our second observation is that the all-reduced communication operation during the backward parameter synchronization step takes up most of the training time in each iteration. Specifically, it can account for around 53% of the training time for RDMA and 82% for IPOIB, and extremely even 91% for TCP/IP. So this can be clearly seen if we look at the green parts in the figure, which is dominating the training time. So these 2 observations underscore the importance of optimizing the communication operations in the large language model training. So especially when you do have the high-speed interconnects, so you may consider how to utilize them well. And speaking of this, how is our interconnect utilized then? So now let's turn our attention to the interconnect utilization under strong scaling. Please note that the utilization in this paper means the achieved bandwidth in unit of Gbps. So not the ratio or percentage over the hardware speed limit. So as indicated by the figure, our third observation revealed a clearly trend in the interconnect utilization for training those large language models. So we can see that RDMA achieved the highest utilization, ranging from 30 to 60 Gbps. And IPOIB follows with a utilization between around 17 and 20 Gbps. And lastly, the TCP/IP has the lowest utilization, ranging from around like 8 to 9 Gbps. So these results show the superior performance of RDMA in terms of the interconnect utilization. And the one thing to note here is that we have 100 Gbps InfiniBand, and we only have 10 Gbps Ethernet. But the utilization number of the IPOIB is still low, so which could still indicate that there could be some problems for TCP/IP over the high-speed interconnect. And our first observation highlights that the large language models tended to have higher interconnect utilization requirements. So specifically, the GPT-2 large, which is the largest model in this paper, consistently achieved the highest receive and the transmission speed with an average bandwidth of around like 30 Gbps with the 3 different interconnects and the protocols during our experiments. So this indicates that as the model size increases, the demand for interconnect bandwidth also increases. So these observations again emphasize the importance of using the high-speed interconnects in achieving efficient training of these large language models, especially when your models are getting larger. Our second part of experiments focus on the weak scaling aspect, where we keep the macro batch size same for each GPU. So let's take a look into the training time breakdown under weak scaling. Here, our observation 5 is that the forward and backward compute time remains near consistent and can achieve 97% and even 99% in the weak scaling efficiency, which is very high for the distributed training. So this indicates that the computational process in large language model training can scale very well and very effectively under the weak scaling. So with that, our observation 6 is that in weak scaling evaluation, the all-reduced time for large language model parameter synchronization remains heavily influenced by the protocols and the interconnects. So we can see that RDMA promotes around 2.5 times faster training iteration than the IPOIB. And if we compare it with the TCP/IP, the performance difference further enlarges to around 4.79 times. So this once more underscores the importance of the interconnect for efficient training. So with these above observations, we can also have our observation 7, which means that the network communication plays a crucial role in large language model training for both strong scaling and weak scaling. So in the weak scaling, the all-reduced time still takes up a significant portion of the iteration time, so accounting for up to 50%, 80%, and again, even 91% for RDMA, IPOIB, and TCP/IP respectively. So this again highlights the need to optimize the network communication for efficient large language model training. And similarly, let's now examine the interconnect utilization under weak scaling. So our 8th observation reveals that the interconnect utilization under different protocols and the interconnects in weak scaling is analogous to that in strong scaling. So specifically, RDMA achieves interconnect utilization ranging from around 38 to 56 Gbps, and the IPOIB ranges from 17 to 20 Gbps. And finally, TCP/IP ranges from 8 to 9 Gbps. And this observation highlights the consistent performance advantage of RDMA over the other interconnects and the protocols, regardless of the scaling approach. And lastly, we also evaluated the cases where we increase the batch sizes until out-of-memory issue happen. This will increase the computation time and therefore squeeze the ratio of the communication time in the whole training time. And the heat map on the right shows the lower bound of this reduction. So now let's take a look at the impact of larger batch sizes on the communication time during the distributed training. So from the heat map, it shows that the communication time can still take a significant portion of the whole iteration time. So even when we increase the batch sizes, and in fact, this communication time proportion can still occupy at least 34% of iteration time. So with the only exception of the BERT large model. So because it is the smallest model in this paper, and therefore it can go with a much larger batch size of 256. And even in this case, its communication time can still take around 30% of the iteration time. So to conclude, it is important to note that the communication time remains a critical factor to consider. So even when we optimize the batch sizes for training efficiency, and this highlights the need for efficient communication strategies in distributed large language model training. So especially when we are dealing with larger batch sizes. And now that I have shared the evaluation results and the key observations from our study, so let's move on to the final section of my today's presentation. In this section, I will summarize our contributions and discuss some potential future work in this area. In conclusion, our study explored the role of communication in distributed large language model training, and we hope our results can inform the need of design and the development of some efficient systems for training large language models. And we made some several pivotal observations. So both strong and weak scaling exhibit similar trends, and the influence of interconnects and the protocols is crucial. And for the forward and backward compute time, they can scale well, but there are scalability challenges for the communication during the backward propagation process. And the faster interconnects and the protocols such as the RDMA significantly reduce the training iteration time. And additionally, large language models with more parameters tend to show higher interconnect utilization requirement and indicating room for further improvement. And looking ahead, we plan to investigate other parallelism methods, such as the tensor and the pipeline parallelism in the future. And we also aim to explore distributed training behavior for larger models and at larger scales. And finally, we intend to develop some techniques to further optimize the interconnect utilization. So with these efforts, we hope to contribute to the ongoing research in the field of the distributed deep learning and provide some valuable insights for the efficient training of these large language models. And with that, I will conclude my presentation. Thank you so much for your attention today, and I am open to any questions and comments. Thank you.
Thank you very much, Hao. That was great, and a big virtual round of applause to you. We actually have a few questions, so I'll just read them to you now, if that's all right.
Okay.
First one is, by RDMA, do you mean RDMA over IB or Rocky V2?
Yeah, by RDMA, I only mean the RDMA over the infinite band. Yeah, I didn't include the Rocky in this experiment. Mm-hmm.
So no Rocky. Okay.
No Rocky.
Yep.
Mm-hmm.
All infinite band. Interesting. Okay. Yeah, and Taylor has a question. Have you considered adding artificial network noise into the study to explore the impact of performance variability for faster versus slower networks?
That's a very good question. So actually, this is just some like a startup experiment, like I mentioned. We are still have like an ongoing research, and your comment, I think, is definitely a good way to go. Yeah, we can consider that in the future. Yeah.
Yeah. All right, and we have a few questions from Samuel. I'll just take them one by one. So the first is, how would hierarchical interconnects like NVLink plus RDMA over IB impact the conclusions?
I think, again, yeah, this is a very good question. But as I mentioned, due to the limitation of the paper content, we didn't consider like that, include that result in the paper for now. But in the future, that's definitely like one of the future directions. Yeah, we can consider like a large scale, different hierarchies. Yeah.
I see. So I actually missed that throughout the talk. The system you had 2 GPUs per node, but those had no NVLink. That's correct.
No NVLink, correct.
Okay.
Yeah, they are connected through PCIe. Yeah.
Good to know. Okay, Sam's second question is, what is the intuition behind RDMA outperforming IB for LLM training? Is this dependent on the number of GPUs per nodes?
Theoretically, I think RDMA should be like outperforming the IPO-IB and also as well as the TCP/IP. And again, our intuition are not only behind this part, but also throughout the whole work, is that we, during our like daily experience, we find many people, especially who are not doing research with the interconnect or the communication, they ignore the important influence of the different like interconnects and the protocols during the training. They just simply like go online, look for some like a tutorial and then do the training. And then they see that, oh, our training performance is so bad, but they don't know the reason why. So this is why, this is what motivated this research for us to take a look into how much does the communication influence or take part in during the training time of a big model, especially the emerging large language models? Yeah.
Yeah, well put. Okay, so Samuel's third question is, based on your experiments, is there a way to model the performance difference of RDMA over IB networks of the same specification?
That's a very, very good question.
For example,
Actually,
100
yeah,
gigabit.
modeling the training performance of these different interconnects or protocols is also like one of the ongoing direction. So that will be very useful, because I think like for now, throughout the whole community, not many people are aware, like I mentioned, not many people are aware of the performance difference among them. So if we can really do some like modeling work, that will be very interesting.
Yeah, I agreed. And I thought one of your last slides really captured it well, the trade-off, right? And the need for models, like for instance, maybe you're spending too much time on all reduce, but you can help matters by having larger mini batches. But you go too far, you run out of memory.
Yes.
So it's very interesting
Yeah,
work.
you sacrifice the memory, but you get more like a communication time. Yeah.
Yeah, and I'm interested to see if the same conclusions comparing strong and weak are applicable for model-based parallelism, which sounds like is also future work, right?
Yeah, different like a parallelism method. Yeah.
Yeah. Well, great. Thank you very much. I think that's all the time we have. So again, big virtual round of applause to our speakers. Thanks for all the great questions.
Thank you.
And I think that concludes things for today. If I'm not mistaken, we'll have some closing remarks from Matthew Dosanjh. Do we have Matthew? We may not have Matthew available, but Taylor, do you want to close us out?
Yeah, sure. Matt, if you I don't know if there's internet connection problems or something in real life, but this was a fantastic session, and what an amazing way to end the conference. Technical content. Tomorrow we have an amazing set of tutorials. I highly encourage everyone to check those out. Go to the Hot Interconnects program, or you can also find them on the Zoom lobby. So there's something there for everybody. When I was looking at it the other day, it's, introductory content. If you're new to networking, there's machine learning, there's you can go deep into protocols and libraries. There's smart NICs, DPUs. So it's going to be a lot of fun, and a great way to expand your knowledge. On top of that, I think I really want to thank our sponsors again. I really want to thank all the people that were able to provide just top-notch presentations. This has been an amazing conference, and I encourage everybody, if you are interested, to participate in this conference next year. You can reach out to us at hoti.info. That's a great way to go. And hopefully I'm not missing anything else, but again, I look forward to seeing you all at the tutorials tomorrow. And maybe I'll tease that I think last I checked, we were at 945 registrants for this year's Hot Interconnects. That's an incredible number. I'm hoping after tutorials tomorrow that will hit 1,000. So again, it's been absolutely fantastic, and thank you all.